again, we know that the slope is the same for both, but I just want the displacement. All right, I don't want this to take a terribly long amount of time, so finish up if you can, so I can pick on some people here. I'm going to pick out 2 people. So, well, I'll start with you, Philip. What was the displacement on the left one?
Would it be 12.5 meters?
All right, so I assume you found the area?
Yes.
All right, so 12.5 meters, no problems. You guys follow that okay? So how many of you found the second one? How many of you did so by breaking it up into 2 areas? Just raise your hand if you broke it up into 2 areas. I'm just interested. All right, so I assume you had to figure out when this was. And you had enough information to figure out when it was because you know the slope. And once you knew the slope, you could kind of iterate over to figure out that that's at the 2-second mark, correct? At the same time, then, you had 2 triangles. So what's the area of this triangle? -2 meters. And what is the area of this triangle? Positive 2.5?
4.5.
I think it's 4.5. But still, positive 4.5. 1/2 times 3 times 3, correct? Now, this gives us a displacement, right? We can read the displacement off here pretty easy. It's 2.5 meters, because that's the total displacement. Went backwards 2 meters, forwards 4.5 meters. What people neglect to see here is that this is still a trapezoid. It's a non-Euclidean trapezoid, but it's still a trapezoid. It's like what would happen if you took your trapezoid and treated it like a sunshade and flipped it over. You twisted it. Same idea. And people don't realize that it still fits most of the definitions of a trapezoid in that there's 2 parallel lines and there's 2 other lines. That's still a trapezoid. The only problem is that it's got an occlusion in the center. We would never call this a quadrilateral because the lines cross in the middle. But 1/2 times the sum of the bases times the height. Base number 1 is -2. Base number 2 is 3. And the height is 5. Well, if we're just going to treat it like a strict trapezoid, that's going to be positive 2.5 meters. Do you follow what I'm doing here? It can still be treated like a trapezoid. The problem is that part of our area is negative, non-Euclid part of this. This is a non-Euclidean trapezoid. Doesn't follow the rules of Euclid's math, but that's okay. I know you don't know those things, and I'm not trying to drive it home. I'm trying to make it clear to you that we can treat the entire area as a single displacement and still use the rule for a trapezoid, and it works just fine. In the same way that this was also a trapezoid, just with one of the bases equal to 0. Well, you get that too. At least I hope you do. That's kind of a necessary skill for what I'm going to do next. Now, if I ask you for the distance, there's no way to get the answer without finding the individual areas. That part, I can't escape that. But if you just wanted the total displacement, you can do it without having to stop in the middle and figure out the separate areas. Before we go on today, I need to express something to you guys that requires a few moments of patience. We are going to be talking about uniform accelerated motion for the next 3 days or so. It's what we really have been studying so far. This is also known as Galileo's rules of motion. And if you haven't come to grips with all the stuff that we've been doing, let's sum it up here. We've been talking about displacement. We've been talking about velocity, both a starting velocity and a final velocity. We've been talking about acceleration and time. We need to have some symbology here. And so for the next few moments, I want to kind of give you an agreed upon set of symbols we're going to use for the remainder of the year. And so to kind of get us all together on that, I want to associate a set of symbols with these words. Some of these are going to be pretty easy. For example, I think we can all agree A will work out for acceleration. Velocity is a little harder though. Not because V is such a difficult term to use, but because we have two of them. If you'll notice, we always refer to the starting velocity and some ending velocity. So I will have two different V's here. For you guys who had AP1 with me or AP1 with somebody else, you probably used a lowercase I and a lowercase f here for initial and final. We're not going to do that in this class, although we will have an initial and a final, and they're both velocities. We're going to put a V with a small circle here to indicate initial velocity, and then just a V by itself to indicate final velocity. The symbology here is to indicate that V naught is actually V when time equals 0. So it's a shorthand for saying that. This little 0 here is pronounced naught, as in naughty, but naught. So I will often say V naught, and I mean initial velocity. Okay? If I say just V, I'm referring to the final velocity. But be careful. Final velocity is a misnomer. It's really the wrong word to use here. It's the velocity at the end of the time interval. It might not be the object's final velocity, but it's at least at the end of the interval for the time in which you are observing it. So be more flexible with your understanding there. Displacement, by definition, is change in position. So in dealing with displacement, I need to remind you of something that you've learned, but it's probably been a while, and that is the delta symbol. Capital delta, the Greek letter, is just a triangle, an isosceles triangle, usually with a harder edge bottom than the top. But what you need to understand is that this symbol you already learned in Algebra 1, and it strictly means change in. So when the delta symbol is put in front of any other construct in any math or physics class, you just put the words change in front of that construct. So if I want to say change in position, I would say delta x. That's what we mean by change in position, where I use x to represent position. And you should already be familiar with this because you probably use something like delta y divided by delta x for slope way back in the day. But if you didn't, I want everybody on the same page for this here. And this does strictly mean x minus x naught. You'll have to be able to substitute the delta x or x minus x naught depending on your circumstances. Remember, these represent initial and final positions over the time interval. Now, these four variables are all the vector variables that we're going to associate with kinematics and motion. So technically, they all should have a bar over the top of them. The bar is a reminder to you and to me that these values represent vectors and therefore, when asked, should include direction. Forwards, backwards, up, down, all that stuff. Now, technically, I should use delta t for time. Technically, I should. I never do. I just use t for the time interval. I should use delta t. That would be better of me, but I'm not going to. And you'll understand why when you start seeing t shows up too often, always have a delta in front of it. So this is the symbology I want to use for now. I want to point out that in discussing uniform accelerated motion, we have 5 motion variables. Good so far? All right. Let's also pull together 2 things that we already have been talking about that now I think are more relevant. Let me get some of this stuff out the way. Rewrite the word displacement. We've talked about finding the slope of a velocity versus time graph. And in that, the slope was the acceleration. Technically, that's what we've been doing. Slope, delta y over delta x, and we set that equal to acceleration. But I can write this as v minus v naught over t using the variables that we have today, at least the nomenclature I want you to use today. Now, just using a little bit of algebra, like multiplying both sides by t, and then solving for v so it's by itself, I produce this relationship. I want to highlight this relationship for a moment because it's a motion equation. Now, you guys from last year think I'm going to say something that I'm not going to say. There are very few motion equations. Galileo's rules are not motion equations. We tend to think they are, and you got told last year that they were. This is a motion equation. And the difference here that I need to emphasize is that a motion equation predicts future events based on current events, based on an initial set of conditions. This is a motion equation because it tells me the future velocity of the object based on knowing some initial conditions that existed at the start of the object's motion, and allow me to substitute in any future time that I want. That's what makes this a motion equation. The reason it's important and the reason why I'm spending so much time emphasizing this is we're going to be doing some calculus in here. Calculus works on the motion equations, but nothing else. So when I have a motion equation, I will often write it a little different to emphasize that it is a function related to time based on other constants. So in this case, the functional importance is that this value gives us events in the future. Now, I want to set that aside for a minute, but I want you to understand that that's a true motion equation. At the same time, we came up with a different relationship for displacement. Displacement was based on the area of a trapezoid. But by now, you do realize that the bases were always the velocities. So I don't think I have to keep saying it's a trapezoid as much as saying that this was the initial velocity and this was the final velocity. And the height was always the time interval. So again, I don't think I really have to do this anymore. I don't have to say it's a trapezoid all the time. Now, this is a similar relationship telling me where the object's going to be, or at least the displacement of the object. But this is not a motion equation. It's a Galileo's equation, but it's not a motion equation. It doesn't tell me a future event based on initial conditions. It tells me what the displacement is, but I have to know what the future velocity is in order to actually use this. So it's not strictly a motion equation. It's not a function related to time. I know it's a subtle difference, But we will not always be doing uniform accelerated motion. Our accelerations don't have to be constant, so we won't always be using Galileo's rules. They're convenient for simplistic looking at motion, but they're very, very limited. And so I need you to start appreciating their limitations. Everything we've talked about so far up to this point this year has been predicated on the idea that the acceleration is a constant. That doesn't have to be true. Now, your problems were related to just these two things. All the problems that you had could be solved using these two things only. But a lot of times, I'm not sure you saw it that way. You were focused on slope and area. That worked really well for the first two questions and then worked less well for the third question. Now, assuming you did the first two with no difficulty, and I know that's a big ask, but what did you get for the acceleration here for that second one? That's right, it was -2 meters per second squared. The initial velocity was 6 meters per second. The final velocity was 0. And they told us that the whole thing took 3 seconds. Sound familiar? What you did? You probably took the area and figured out that delta x was equal to 9 meters. And you took the slope and found out that it was -2. Now, in the next question, you were asked specifically to consider the same ramp. Now, this is a stretch, so you might not have known that that meant that the acceleration stayed the same. Same ramp means the same acceleration. You were then told that the initial velocity stayed the same at 6 meters per second, but that you were to wait until it returned at 8 meters per second. That would be returning, so that would make that negative. The first thing I want to emphasize here is any of the variables with the bars have to have their direction associated with them. And in one-dimensional motion, direction is positive or negative. So if going away was 6, then coming back has to be -8. Okay so far? You were asked to figure out the time and likely the distance or displacement. Now, these were the 3 pieces of information given. If I come back to the motion relationships we just talked about, we had V equals AT plus V naught, and we had delta x equals 1/2 V plus V naught times T. It seems to me that you could put in your variables and see what information can be solved with what you've been provided without having to look at an area. It was difficult to draw this graph because you're given the slope and the starting and final velocity, but not really anything else. We don't need the graph. And this is -8 equals -2t plus 6. That's still the slope formula. And this was delta x equals 1/2 times 6 plus -8 times t. Now, you can't solve this, 2 unknowns, but you can certainly solve this, 1 unknown. Correct? No graph. I don't need a graph. I'm just using slope and area still. Now, the problem is that this question asked for distance, partial areas. That feels like you're probably going to need a graph. And now that you have the time, you probably could make the graph. It's a lot easier to make the graph now. But there might be other ways to figure out the distance. Yes, sir?
Can't you just kind of tweak the formula to say the absolute value of V naught plus the absolute value of V, and then just use that?
Does it work?
I haven't tried it, so I wouldn't know.
Okay, it won't work. And what he's suggesting is could we use the absolute value and plug those in to figure out the total displacement. And the reason it won't work is because if you think of what it actually does to the graph, it creates more area than there actually would be for the motion of the object. So that part won't work. to be quite honest with all of you, the only way you could figure out the distance is either to plot it and figure out the individual areas, or you have to break this up into two parts. You have to figure out how far it goes coming to rest and how far it goes after it was from rest to 8 meters per second. But I don't want to press that on anybody right now. That's a lot. And for the people who have never done this before, let's stay focused for a few more minutes doing just these specific activities, and then I'll show you how to come back and get this question without graphing it. Our goal here is to leave the graphing behind, okay? So, at this moment, do you realize, though, you could figure out the total displacement because you can figure out that t equals 7 seconds. You see that, right? And once I have the time, I can plug it in over here and just get the displacement. Do you guys see that okay? Consider this. I don't care which one of these you want to take a look at, but they can be done without having to draw any graphs. So many of you probably didn't get too far, but some of you probably did. Which one do you want to see? The last one or the second to last one? Yes, sir.
The last one.
Okay. Now, no graphs. Let's just consider what they ask us and what we could do to get a solution. The first thing I want you to consider doing on uniform accelerated motion problems is write out this list. If you haven't noticed yet, the two relationships that we have each have 4 pieces of information in them. Are you noticing that? Which means you can't solve anything without being given at least 3 pieces of information. So there's 3 pieces of information there. Some of it obvious, maybe some of it less obvious. So it says a mountain goat starts a rock slide and the rocks crash down the slope 100 meters. There's only one term here that's in meters, so it's hard to get these wrong. You can't put the 100 anywhere else because it wouldn't make sense to go anywhere else. Only one of these terms is in meters. Starts a rock slide suggests the rocks weren't sliding before. That's a subtle thing, but that tells you something, doesn't it? How fast were the rocks going before they started sliding? I think 0 is not a big stretch. And we're told that it takes 5 seconds for them to reach the bottom. I think we can figure some stuff out here, don't you? Not only do I think you can figure out the acceleration, but I'm pretty sure you can figure out how fast they're going when they reach the bottom too. And let's just take a look. I've got V equals A times 5 plus 0. No help there, right? And I've got delta x equals 1/2 0 plus V times 5. Not a whole lot there either. And there's 2 unknowns in both. But my understanding is that you guys have had a little bit of algebra. So if I have 2 equations and 2 unknowns, I'm pretty sure I have a method to get to a solution, don't I? I'm thinking substitution. Are you seeing substitution? I'm thinking substitution. Because we know things. So yeah, delta x equals 1/2 0 plus 5a times 5. Oh, and delta x is what, 100? I forgot delta x is 100. I might not have even had to do substitution. But they wanted the acceleration, so this is a way to get to acceleration without knowing the velocity. Now, you might have found the velocity and plugged it in to get the acceleration. That would work too. But there's a reason why I would consider doing this. And I want you to see something, if you would just bear with me. I am confident in your ability to figure out the end of this problem. So you guys should get 8 meters per second squared. Is it plausible you could be asked this question again in a similar way? And you'd have to do the substitution to get the acceleration. Or you'd have to solve for the velocity and then plug that in to get the acceleration. 2 steps. I want you to note that you don't have to do things like that. You guys have had more than enough algebra to recognize that you can use algebra symbolically to create new ideas. This relationship has everything in it except for displacement. And this relationship has everything in it except for acceleration. It's possible to create other relationships. For example, I might want a relationship that doesn't have the final velocity in it. That might be a useful thing for me to have. Because like in this problem, I didn't know how fast the rocks were going. And to get that answer, we had to do substitution, but we could do substitution right now without any numbers. That's the beauty of algebra. I took all of this and put it where V was. Now, I know if you guys new to this is a lot perhaps, but I can expand that. Inside here in the parentheses, I'm going to get AT plus 2 V naught. I can distribute the T, and I can distribute the 1/2, and I'll get delta X equals 1/2 AT squared plus V naught times T. I've created something new. This is a new relationship that has 4 motion variables in it, but is missing the final velocity. Now, you guys who were in a physics class before, you know what we're doing here. And you should know the 5 things that exist here. For you guys who are new to this, you should be seeing something happening here. I have a new relationship that has 4 of the motion variables, everything in it except for final velocity. It joins the other 2, which again have 4 motion variables, each missing 1 of the motion variables. Do you see that so far? So there's probably 2 more of these. One where we eliminate the initial velocity, and one where we eliminate the time. There are considered to be 5 Galilean motion equations. These motion equations are all combinations of the motion variables, and they strike at our ability to solve simple kinematics questions. They're not physics, not really. They're what happens when you study uniform accelerated motion. They are the result of taking a look at the area under the curve and taking a look at the slope. That's all they are. But, and I need to emphasize this one and this one are actually special. And you should emphasize that they have higher level importance. They're related in ways other than algebra. Those are true motion equations. They don't look like it, but they are. Again, if you look closely, This one's based on initial conditions and only initial conditions. Tells us a displacement, where the object will be at some future time, and it's a function of just t. It's an actual motion equation. And it's important to me that you notice that. Now, it is equally important that you realize that the reason we did this substitution wasn't because I think it's a great exercise in algebra. If you look up Galileo's motions equations, it'll show you the 5 equations. But it's not about the equations. It's a method for solving problems. Every motion problem gives you 3 pieces of information, which means there's always a motion equation that can be used in one step to solve for the missing piece. That's what you need to see. It's not obvious what you would do to get the other motion equations. You would probably solve this for initial velocity, plug it in here, and that would give you another motion equation. Or solve this for time, plug it in here, and that would give you another motion equation. And you should try that. But even if you don't feel like trying that, by the time you come in tomorrow, you should have all 5 of these. It's not hard to do, and I would expect that if minimum, you could use the tiny internet and find them all. If you type in Galileo motion equations, you'll get them. But I want to emphasize something. They are not motion equations. They can be used under only one condition, and that is when the acceleration is constant. And they can only be used for one acceleration at a time. So if you are in your car and you hit the accelerator and you speed up to 50 miles an hour, and then you hit the brakes and slow to a stop, that has to be 2 separate problems because there's 2 different accelerations. There's the acceleration when you're speeding up, and there's the acceleration when you're slowing down, 2 separate problems. They're very limited in what they can do, but they're functional. Consider this question. Sorry, we don't have that one. So as long as you don't have that one, this is a typical, like level 1, simple as it can be, motion problem. All motion problems are going to give you 3 of the pieces of information and ask for a 4th or a 5th. They're all there. So, man throws the ball upward, it rises 10 meters before stopping and returning. If the acceleration is 10 meters per second squared, how fast did he throw the ball? These problems should always be easy to identify as being motion problems. They're going to give you things like displacement, velocity, times, accelerations. They're going to give you some of the obvious things. What you should be endeavoring to do is figure out which of the 3 they've given you in order to solve for the one that is being asked. There are several things you should do at the start of a problem like this. Like establish what direction you want to be positive. Is upwards going to be positive, or is downwards going to be positive? You can choose this. I'm going to choose upwards to be positive. That's something that has to be applied to any of the variables that have the bar. Now the ball went upwards 10 meters. the ball comes to rest. The ball experiences an acceleration of 10 meters per second per second. But gravity pulls things downwards. How fast did he throw the ball? This is a motion equation problem. It's got all the telltale signs. Now you happen to want to use it, you happen to want to solve for one that doesn't have time in it. We don't have that relationship. Your only way of doing this is to use both equations and do substitution until you figure out how to get rid of that and just find one equation. Now, I don't want to make this whole class about doing these kind of math problems. These are the least interesting thing that there is in physics. But the sooner you can master these, the sooner we don't have to do them anymore. So I'll tell you that the start of this problem is probably to use both relationships. 0 equals negative 10t plus v naught. Or 10 equals 1/2 v naught plus 0 times t. That's all you got. So you're going to have to do some substitution. Or for you guys in the know, you remember that there might be an equation out there that already has eliminated t. It might exist out there somewhere. It might. I mean, I don't want to take away your fun times and looking it up. But now you're down to just one more. The Galilean motion equations aren't interesting. They're not even that insightful. I will, however, require that you memorize them by the end of next week. So, score some points tomorrow. Come in with all 5 of them. You can either crack open the book, break open the little internet, I don't know, ask somebody from last year, pull out last year's notes. Look on a poster hanging in another physics classroom. I've taken all of mine down.